first kind of unsupervised problem that we're going to look at is known as clustering. This is closely related to the problem of classification. We're going to assume that the data naturally segregates into some number of classes and that those classes are reflected in the feature distributions. So essentially, samples from objects of the same class are closer together in feature space to each other than they are to samples of other classes. Note that for this simple criterion, the criterion of proximity, to work and give reasonable answers, the clusters associated with the different classes must be reasonably well separated in space and need to be reasonably convex. It's not possible with this kind of purely distance-based approach to separate classes that intertwine or surround each other or that kind of thing. So the statement of the problem that we're going to attempt to solve is, given some data and some target number of clusters, K, find the optimal partitioning of the data samples into that many classes. Obviously, it's a slight drawback having to specify the particular number K, but it does make the problem a lot more tractable, and we can consider the problem of choosing the best K as a distinct problem from the problem of finding the best partition into any given K. For our simple distance-based definition, we can define a loss function to assess any particular cluster assignment. We'll define a candidate solution to the problem as follows. We have K cluster centroids, which are simply vectors in the feature space, labelled C1, C2 up to Ck. And we will also have N cluster assignments, one for each of the samples in the training data, and we'll call these A1, A2 up to AN. So those are just integers identifying which cluster each sample has been assigned to. The loss function that we wish to minimize then is just the sum of the squared distances between each of the samples X and the cluster centroid to which it has been assigned, which we can express like this. This is also known as the within cluster sum of squares. So there are an awful lot of possible assignments that can be made, roughly K to the N. So for any reasonable sized data set, this gets really large really quickly, and so an exhaustive search is not practical. Instead, we can apply various heuristic methods, of which the most well-known and popular is known as the kMeans algorithm, sometimes the naive kMeans algorithm, and also goes by a few other names, such as Lloyd's algorithm or the Lloyd-Forgy algorithm. This algorithm is extremely simple. It just proceeds iteratively, and at each step we perform two different operations. The first step is an assignment step, and in this step we just assign each sample X to its closest centroid from the choice of K centroids. In the second step, we update all the centroid locations to be at the mean position of all of the samples that have been assigned to them. We keep repeating this until no assignments change. Here is a simple example of this in action over a few steps on some simple data. We can see that the cluster assignments pretty rapidly settle down to their final form. This kMeans algorithm is extremely easy to understand and very easy to implement. It's also guaranteed to converge on a solution. It's not going to loop forever. It is not guaranteed to find the optimal or even a particularly good solution. In fact, it's very easy to construct pathological examples for which the solutions produced by the naive kMeans algorithm are quite terrible. Some of the issues with the kinds of solutions that the algorithm finds are, well, first of all, because it uses a kind of uniform distance-based loss, it's biased towards finding roughly spherical clusters of similar sizes. If this doesn't align well with the kind of distribution of the data, you can very easily wind up having things that clearly should be in one cluster actually assigned to a different one. Because it's based on a simple Euclidean distance metric, it suffers from similar kinds of problems that we've discussed before when you go into high dimensions, and it's sensitive to differences in the scale of the different feature dimensions and also into variations in how noisy those feature dimensions are. And in particular, the solutions that it finds are extremely sensitive to the choice of initial cluster assignments. So having a good initialization scheme can make all the difference between it finding decent clusters and not. The other obvious problem is that you need to choose this hyperparameter K. Now, in some cases, the choice of this may be obvious from the nature of the problem or from simple inspection of the data, but often that won't be the case. We can't naively learn K along with the fitting process because increasing K always enables us to bring the loss down up until the point where K reaches the number of distinct points. We can always add a cluster with zero loss, which takes away the loss from some other cluster by locating it exactly at some data point. We may still be able to use this kind of approach in combination with some penalty criterion, such as the Akaike information criterion or a Bayes information criterion, that essentially penalizes the number of parameters in the model, where in this case we can consider the number of clusters to be equivalent to the number of parameters because you have to define a centroid for each one. Failing that, we can apply the usual processes for hyperparameter tuning. Essentially, try a bunch of different values and validate or cross-validate to assess their relative merits. Because the kMeans algorithm is highly sensitive to initialization, a number of different initialization schemes have been proposed. One very naive one, which actually isn't used very much, is just to randomly pick your initial centroids from across the feature ranges. The problem with this is that the centroids are not constrained to be close to any of the actual data samples. And as a result, you can wind up with situations where some of the clusters are empty. Probably the simplest and most common initialization scheme is just to randomly choose the locations of particular samples in the training set as the initial cluster centroids. This guarantees that they will be close to at least some sample, but it doesn't guarantee a good distribution across the range of possible sample values. A more sophisticated and well-supported initialization scheme is known as kMeans++. Essentially, it still chooses random samples to be the centroids, but it chooses iteratively. The first centroid is chosen completely at random. The second choice is chosen randomly, but with the random choice weighted by the distances of the samples from that initial first centroid. So you're more likely to choose a second centroid, which is quite a long way from the first one. You then proceed iteratively at each step, finding for each sample in the training set its nearest of all the centroids you've specified so far, and then weighting it according to its distance to that nearest centroid. Overall, this process weights the centroid choices to be reasonably well distributed through the data set. So kMeans is very widely used, and the most common applications are finding clusters in scattered data samples, pretty much as you would expect. Some slightly more interesting applications come from domains like computer vision, where you might be dividing up the pixels in an image according to their similarity. So one application of this is color quantization, where you have an image in loads of colors and you need to find a small number of colors with which to best represent that image, for example, for printing purposes or for compression. K-means clustering is widely used for this kind of approach. A very similar approach is when you use it for image segmentation. Again, you're finding regions of color similarity and associating them with distinct objects in the image. A closely related application is finding objects in moving images, in videos, by looking at their similar movement patterns. So collections of pixels that are moving together in a very similar way can be kind of heuristically assumed to be parts of the same objects. There are a number of alternatives to basic K-means clustering. One obvious change is to use the median to define cluster centroids, and then to use the L1 distance for cluster assignments. A similar sounding method, indeed often confused, is the kMedoids clustering. In this case, it's similar to k-medians in the way that you do the measurements and assignments, but instead of assigning the centroid by finding the median position of all of the features independently, you instead constrain the centroid, or rather the medoid, to being one of the actual sample positions. So the centroid is assigned to be the sample that is least unlike all of the other samples in its cluster. The requirement then is that the cluster center must always be one of the samples in the data. Both k-medians and k-medoids are more suitable than k-means if some of your feature dimensions are discrete values rather than continuous. And k-medoids in particular is relevant when you need the clusters to be related to actual samples. So for example, if you're using the clustering to guide resource allocation, to put people in buildings, or allocate supplies of particular resources to particular locations, then you can't just magically create a location which is in midair. You need to go to a real building or whatever. Another set of alternatives to k-means clustering are hierarchical clustering methods. Instead of assigning all of the clusters in one go, these instead assign them incrementally, either in an agglomerative fashion, where you start with all of the samples and then you join together the two closest into one cluster and keep doing that until you've joined everything into one huge cluster at the end, building up a kind of tree of joinings. Or alternatively, it can be done in a divisive fashion, where you start with all of the samples in one cluster and you optimally divide it into two clusters and recursively do the same until you've divided all the way down to the leaf samples. This is extremely conceptually similar to the decision tree fitting that we talked about in week 3. These kind of hierarchical clustering trees can often be represented in what's known as a dendrogram, which looks like this. And to define the optimal clustering for any given number of clusters, you can just cut the tree at the chosen level. The two-step iterative process of the k-means algorithm, where you first assign to cluster centers and then you update those centers, is an instance of a more general pattern that we will see repeatedly in unsupervised learning. And the more general form of it is known as expectation maximization. So there are two steps which are iterated alternately. In the first step, you make some predictions based on your model, and in the second step, you update the model based on the predictions. We'll talk about this a lot more next week. You could also say that the forward pass, backwards pass structure that we use when training a neural net falls into a very similar category of algorithm. The forward pass is making predictions based on our existing model. The backwards pass and then the update will make an update to the model based on what we found out from our predictions. Of course, in the case of the neural net training that we've discussed so far, there will be some supervisory labels which we'll use to guide the training process.